Um, Thank you. Hello, ladies and gentlemen. I hope you are fine. I am Saman Momeni, PhD of Mechanical Engineering. And now I want to talk about my research article with this title, An Investigation of Material Effects on the Dynamic Behavior of Composite Materials Incorporated with MR Fluid using an N-layer model. Please. Excuse me, can you? Okay. At the first, I want to talk about the outline of this project. At the first, I want to talk about the motivations and the history of the MR fluid, layer-wise modeling, and the fabrication of the composite structures. And in next step, I want to talk about the experimental setup and the experimental for calculating the dynamic behavior of MR laminated beams. And after that, I want to talk about the material effects on the structures. And at the end, I want to talk about the conclusions. Laminated composite beams are being used in many engineering applications, such as wind turbine blades, helicopter blades, arms of the robots, satellites, and many other engineering applications. And in next slide, if I want to talk, excuse me, please. Next slide. And in next slide, I want to talk about the advantages of composite structures. Composite structures have many advantages compared to other materials, such as metallic counterparts. For example, higher strength, higher stiffness, and the low weight. And most of the time, the thermal insulation is more better than other materials, and maintenance, fuel, and cost is very better, and sometimes less than other materials such as metallic counterparts. In next slide, I want to talk about the history of the MR fluid. Before that, after a period of time, the composite metallic counterpart structures suddenly exposed to harsh or random vibration. And after a period of time, as you can see in this figure, we have not a good idea, or we have not a good happen. In order to increase the, excuse me, in next slide, next. Thank you. In order to improve the natural frequencies of the structure, in my opinion, MR fluids is the very good candidate for doing this. MR fluids are a new category of intelligent materials with individual components. As you can see in this figure, by applying the magnetic fields, the molecules of the MR fluid changed, and you can manage the natural frequencies or stiffness of the structures. And MR fluids have the carrier fluids, ferromagnetic particles, surfactants, and additives. And in next slide, if I want to talk about the layer-wise modeling of the structures, the complex shear modulus of the structures are calculated based on this formula, the summation of the G prime and G second. G prime and G second is dependent on the magnetic field intensities and the natural frequencies. And please click it. And excuse me, can you click it? And in order to determine the G prime, we need to calculate the G prime and G second. Based on the standard test, ASTM E756, we can calculate G prime and G second. And in next slide, if I wanna, excuse me, In next slide, if I want to talk about the new layer of n layer of the layer-wise theory, the thickness of the nth layer is defined from minus half of h of n up to half of h of n. This theory was published in my previous article in other journals that consist of the layer-wise theory of this model. And the displacement of the nth layer is defined as this formula. And based on this formula, U0 and W0 are the translations of the first layer of the composite structure. And phi of x of n is the rotation of the nth layer about the x-axis. And this figure shows the arrangement of the composite structures from the first layer up to nth layer. And in next slide, by considering the Hamilton principle, we can calculate the equations of motion of the structure. Based on this equation, delta of U is the virtual strain energy, and delta of K is the virtual kinetic energy, and delta W is the virtual work. And as you know, the displacement of the laminated composite of the layer-wise modeling is calculated based on this formula. And in next step or next slide, I wanna talk about the fabrication of the, before that, the equation of motion of for nth layer of the MR laminated beam is calculated based on this formula. And in next step, I want to talk about the equation of motion for the 5 layer of the MR laminated beam. In next slide, by putting the n is equal to 5, we can calculate the equations of motion for 5 layer of MR laminated beam. And about the finite element of this model and the equations of motion, I published another journal in that you can see if you want. And in next slide, in order to determine the experimental setup, and experimental natural frequencies of the structures, at the first, with 8 layers of e-glass material, fiber carbon, and Kevlar that have been cut into the spatial dimension. And after that, by hand layup method of the resin into the different layers of the composite. After that, this section, you should place the structure into the autoclave for 560 minutes at 85 degrees centigrade. And after the time, in next slide, you can see the structure, and you can cut the composite structure into the spatial dimension with special strips in order to build the MR laminated beam for different layers. If you click it, okay, sample of MR laminated beams without MR fluid, you can see in the right figure. And by injection of MRF 162 built by the Lord Corporation between the layers of 2 and 4, you can build the MR laminated beams for different materials. After that, in next slide, in order to determine, as you can see, This slide shows the composite materials built by e-glass, Kevlar, and fiber carbon materials. And after that, we want to compare the materials with each other. Please, thank you. In order to determine the experimental of MR laminated beam or experimental natural frequencies, dynamic behavior, in order to determine the dynamic behavior of MR laminated beams in a clamp-free boundary condition, a tiny accelerometer, as you can see in this figure, a tiny accelerometer is attached at the free end of the beam in order to determine the dynamic behavior. And the shaker is used to generate white noise with power spectral density of 40 decibel in the range of 0 up to 800 Hertz. And the resolution of this instrument is about 1 Hertz. And the magnetic fields varies from 0 up to 2100 Gauss. And the arrangement of the composite and MR fluid and the width of the composite and MR fluid are showing in this table. After that, please, thank you. This slide shows the numerical example of for FRF of different composite materials built by Kevlar, fiber carbon, and e-glass material. The peaks of the peaks on this graph show the natural frequencies for different modes of the MR laminated beams built by different materials. As you can see, it's obvious that the natural frequencies of the Kevlar is much more bigger than fiber carbon and e-glass materials. And after that, please, can you, thank you. The mechanical properties of different composite materials, as you can see in this table, shows that the E11 and the density of the e-glass are very lower than fiber carbon and Kevlar. And this phenomena shows that Kevlar is very harder than other materials such as fiber carbon and e-glass. And because of that, the mechanical properties of the Kevlar is bigger than two other materials. And in next slide, if I want to talk about the effects of the composite materials on natural frequencies, and first three natural frequencies shows that natural frequencies of the Kevlar is about 80% bigger than e-glass materials. And natural frequencies of the fiber carbon is about 20 up to 25% bigger than e-glass material. And as you can see in next slide, all of materials such as fiber carbon, e-glass, and Kevlar follow this rule. And by applying the magnetic fields up to 1,400 Gauss, the amounts of natural frequencies increased. But after that, up to 2,100 Gauss, this amount suddenly decreased. This phenomenon is dependent on the nature of the MR fluid. If you wanna to change the dynamic behavior of the structure, in best situation for you can choose this condition up to 1,400 Gauss. And if you please as I said that this slide shows that the natural frequencies of the e-glass material by applying the magnetic fields, and the comparison of the experimental with new layer n layer of the layer-wise theory and experimental with FSTT model. Deviation percent, excuse me, please. Excuse me. And deviation percent in this table shows that the accuracy of the n layer of the layer-wise theory is much more accurate than the FSTT. As you can see, the deviation percent of the n layer of the layer-wise theory versus experimental and FSTT versus experimental is about 40% lower than the FSTT. And this phenomenon is shows that the layer-wise model is much more accurate than other methods. If you select in next slide, the comparison of the natural frequency, same as the previous slide, for fiber carbon are showing here. The phenomena is same as the previous slide, but the deviation percent for harder materials is much more bigger than softer materials. And in next slide, as you can see, this phenomena shows that the deviation percent of the Kevlar is much more bigger than the fiber carbon, and fiber carbon is much more bigger than e-glass material. But other rules, for example, up to 140 Gauss is same as each other. If you select the next slide, excuse me, if I want to talk about the percentage improvement of the material by applying the magnetic fields, for example, in this slide, f of h is the natural frequencies of the structure by applying the magnetic field, and f of a is the natural frequency of the structure without applying the magnetic fields. Same as the previous, delta f for the harder material is bigger than softer materials, but up to 1,400 Gauss, this amount will be increased. And after that, by applying the magnetic fields up to 2,100 Gauss, this amount suddenly decreased. And if you select the next slide, yes, this graph shows this phenomena that delta F of the Kevlar is much more bigger than the fiber carbon, and the e-glass material has the lowest amount of delta F or natural frequency in this slide. And in next step, if I want to talk about this article briefly, dynamic behavior of the MR laminated beams for different materials have been investigated based on the N layer of the layer-wise theory, and the dynamic response of this structure compared with FSTT, and by applying the magnetic fields on the structure, the amount of percentage of the harder materials is much more bigger than other materials. And the percentage improvement of the Kevlar has the highest and e-glass has the lowest. And as we talked about, by applying magnetic fields up to 1,400 Gauss, the natural frequencies of the structure has been increased, but after that has been decreased. The present work shows that designers and manufacturers of the structures can optimize the materials by selecting the low-cost materials and applying the magnetic fields. Many thanks for your consideration. If you select the next slide, thank you. If you have any question,